I'm Alona Fyshe. I'm a computer scientist, and so when David asked me to be part of this, he was, I think, looking for somebody who was on the side of data. Certainly, I believe data is a strong thing, but I think we can play well together. I think data and theory go hand in hand. Next slide. So do we need more data or do we need more theory? I think we actually agree on the answer. The answer is, next slide. Yes, this is going to be terrible. My jokes are going to be just not very funny. Keep going, okay. Okay, so I think, so what I'm going to talk about today is actually a way that we can marry data and theory. Oh, okay. Okay, good. The way we can marry data and theory in one model that allows us to fuse it together. And so that we don't have to choose. We can allow our model to choose data when there's enough data to make the choice reasonable. So I'll start with a really simple example. Let's say I give you a coin, and the task is, can you tell if this coin is a fair coin? So is it loaded? Does it show heads or tails more often? And so you go out into the world and you're going to flip it 6 times. You get 1 head and 5 tails. So you already have some evidence that this is not a fair coin, and you may have noticed that it's a Canadian quarter. So it's 19 cents on your 25 cents. So things are not going well for you. So you probably learned at some point in your life that in order to estimate, let's say theta is the probability of getting heads, you should take the number of times you saw a head and divide it by the total number of flips. And so if you do that, you get 0.167. And the reason, you may not know this, but the reason why you have been taught to do that is because that number, 0.167, is the maximum point on this curve. It is the x value that gives you the maximum point on this curve. So you have been taught to maximize the likelihood of your data by changing this parameter theta. So the setting of theta that maximizes the likelihood of the data you observed is the heads over total number of flips. So this whole time you were optimizing. Eve, I don't know what you think of that. Okay, so this is the maximum likelihood estimate. We are maximizing the likelihood of the data that we saw. So the maximum a posteriori estimate allows us to blend data with some belief we have about what the coin should be doing, if the coin is fair or not. So let's say you believe the coin is fair. You trust me as a Canadian that the coin I have given you is not loaded. And so you have a prior belief that the setting for theta should be 0.5. So you think that the curve should look more like this. This is your prior belief. And what we would like to do is be able to blend it with the data that we saw. So we're going to want to try to take these two curves and merge them together, to take our data and our theory and make them one. And so that's the maximum a posteriori estimate. So here we have our prior on the very left-hand side, then our data, and then the blend of the two gives us a value for theta that's somewhere in between. So our value for theta here is 0.42, and that's pretty close to our prior. And the reason it's close to our prior is because we have observed very little data. So we only had 6 data points. So who's to say what the value of theta should be? We don't have enough data. So what we can go out is go out and collect more data. So let's say we observe 100 heads and 500 tails. Now we have a new data likelihood curve, and it's much more peaked. So it gives us a much narrower distribution over the sorts of thetas that we would accept to be reasonable. But you should notice that actually because the ratio of heads to tails is the same, we end up with the same estimate for theta, 0.167. But now when we blend that very peak distribution with our prior belief, we're going to end up with something that's closer to the data. We have enough data at this point to move us towards something that respects the data more than the prior. And so our final estimate here would be 0.171, which is closer to our original 0.167 value. So the map estimate is this theoretical framework for thinking about how we can marry theory and data. It doesn't have to be one or the other. It can be a theoretical framework that gives us the ability to respect data. So now I'm going to talk about one use case, which is image classification. So this is from computer vision. The idea here is we would like to look at one of these images and tell what kind of object is pictured in the image. And so the big data set for this particular task is called ImageNet, and it has a whole bunch of different classes in it. So it's about 1 million images and 1,000 possible objects that can be in the image. And you can see from this set of, this subsample of the images that there's a wide variety in the kinds of things and the sorts of situations we see the things in. So there's some butterflies and some boats and so on and so forth. So I'm going to talk now about a time when using a model that had no ability to sort of respect the data and it was purely theory-driven, was held back a particular area of computer science. So this ImageNet task of trying to tell what object is in an image is incredibly challenging. It's so hard that most of us probably could not do very well on the task, and that's because the actual granularity of the things we have to classify into is very fine. So for example, here this is a subset of the trees in the ImageNet. And there's things, I'm sorry, it's hard for me to read from here. American white birch, downy birch, alder. I probably couldn't tell those apart. Possibly some of you could, but probably most of us could not. And so we're asking this computer vision algorithm to do something that's actually really hard. This is a difficult task because of the granularity of the classes. And in addition, even within the classes, the sorts of images we get are very different. So this is just images of cats, but we have a bunch of different kinds of cats. We also have occlusion, so one of the cats is behind a pillow. And we have different views. We have a view of a cat that all you can see is its face. We have a view of a cat from above. So you can see how this would be a difficult task. This is a difficult task for a computer to do. And so traditional computer vision approaches were sort of a handcrafted pipeline that had been developed long ago, a decade ago. And the idea was we're going to look for key features in the image and extract them. And I know, as a computer scientist, what a key feature looks like. So we pre-program what we're looking for. And these circles on the image show you where the key feature is for that particular image, and the size tells you the scale of the key feature, and the edge tells you the orientation of it. And so we can produce sort of a histogram of these particular features, and it allows us to classify what's in the image, even if it was a picture of the same building but from a different angle. So they ran, when they released ImageNet, they started running these competitions where they would have everybody show up with their algorithm of how to do image classification. And so they ran it in 2010, and the very first time they ran it, somebody got over 70%, which is phenomenal. That's amazing performance for this difficult task. And then in the next year, they got slightly higher. And then in the following year, 2012, somebody came along with an algorithm that was able to respect the data in a different way. So the idea of a convolutional neural net, which is the algorithm that would go on to do well on this task, is that I don't know what the features are in the image that I'm looking for. I don't know what a key feature looks like. I want you, the data, to tell me what a key feature looks like. So the image comes in on one side, and the algorithm essentially extracts key features and assembles them at different scales. So in some ways, it has some inspiration from the SIFT features, that features can be of different scale. But I don't know what I'm looking for, and I'm going to let the data speak. And so if you run this on natural images, you get out feature detectors that look like this. So they look a bit like edge detectors. But if you run them on, for example, handwritten digits, you get out something that looks more like strokes and dots. So the beginning of a stroke and the stroke itself. So here we're letting the data speak. We have an idea of how that there should be a hierarchy of features, that small features should be put together to make larger features, and that's how we'll do the image classification, but I don't care what the features are. And that's really the main point that I'm trying to drive home here. That if you have the data, you don't have to have a strict theory that puts you sort of in a corner. So here in 2012, the traditional computer vision algorithms did about the same as the previous year. So it had seen that they had hit a ceiling. And then the deep learning convolutional neural nets came the same year and beat them by almost 10%. So a huge gain in just letting the data speak. And then from there on out, so that was Jeff Hinton's team. From there on out, the accuracy just continued to climb, and it's at the point now where it's like 95% accurate, which is a phenomenal feat for this sort of difficult task. And it comes from letting the data speak. And so I think there's a sort of this culmination of ideas coming from computer science where we are allowing the data to speak. So convolutional neural nets take images and create hidden representations of those images, and it turns out that those hidden representations have relations to the areas of the visual processing stream. In addition, there's computational language models, which I didn't talk about today, but do a similar thing. They try to predict co-occurring words in a large corpus. The hidden representations from those models also have a relationship to the human brain's activity when we read words. And then actually there's a relationship between the convolutional neural nets and as well the computational language models. So all around, there's sort of this bubbling up of letting the data speak, and they arrive at a place that's similar, which I think goes to show that it's all about the same thing. It's all about the world. Brain imaging, computational language models, and convolutional neural nets are all about how the world works. So theory versus data, of course, is a false dichotomy. We wouldn't be here if it was, it makes for a better debate if we have a false dichotomy, I guess. But I think what we need theory that's flexible enough to bow to data. So if I could rename this talk, I would have named it Kill Your Darlings. Because I took a creative writing class at one point in my life, where he told us to kill our little darlings. So there is a line in the thing you're writing that is your smartest line. You think it's so beautiful. You think you're so smart for having written that line. And you need to delete it, because it is the thing that's holding you back. It is the thing between you and getting to the true answer, the true best thing that you can write. And so I think that the point I'm trying to make is that we should let our data kill our little darlings. And that's it for me. Thanks.